I hope you'll forgive this characterization right off the bat, but I think of the sexier branches of physics as maybe quantum mechanics, cosmology, maybe string theory. I think these are the areas that really capture the popular imagination, at least. And very few outsiders are aware of plasma physics. And to the extent maybe that nuclear physics has a place in the zeitgeist, it concerns atom bombs and recently Oppenheimer. So how was it that plasma and nuclear physics first caught your attention? So what were the research questions that led you to spend your career in the area?
Well, let me change the epithet a little bit by saying that I consider myself to be an applied physicist. And the fields that you cited as being the ones that you regard as being sexy are the currently fundamental areas of physics that seem to be leading us to brand new knowledge of the laws of nature or the nature of the universe and those kinds of things. So I think that what I'm doing, what I have done in my career, has not been mostly that type of physics. Nuclear physics was once, the cutting edge of discovering the laws of physics, but it hasn't been since, probably the 1960s or 70s. And so what I am doing is pursuing the applications of both nuclear physics, which is nuclear is the name of my department at MIT. I'm a member of the Department of Nuclear Science and Engineering, and that department is interested in the applications of nuclear interactions and nuclear reactions to important things in our society. And I'm also a plasma physicist, which is plasmas are basically one of the key applications of Maxwell's equations, which are the equations of electromagnetism. And so, in that area, I'm studying the ways in which gases of ionized particles, that's what a plasma is, it's a gas of ionized particles, how that interacts with electric and magnetic fields and how it then behaves in very interesting and peculiar ways. And in fact, that has very wide applications. Plasma physics has very wide applications. For one thing, almost all of the visible universe is made up of plasma. The Earth, for example, is a relatively unusual place in having most of its matter not being ionized, unlike stars or galaxies or all sorts of other astrophysical phenomena. And also being very important for applications by us humans to technological development, including, in my case, the possibility of bringing nuclear fusion, the energy source of the sun and stars, down to the terrestrial scale and making it available to humans.
Well, okay. One, thank you at the outset for distinguishing between your work as an applied physicist and then the work on the fundamental aspects of the universe that the other theoretical physicists are working on, because that's important. I don't think I've spoken to an applied physicist on the show so far. It's mainly been theoretical physicists, astrophysicists. So that's very good. I was going to go to start out with just what a plasma is, but you touched on that a bit. And so I'm wondering if we ought to continue for a minute with this distinction between the applied physics and the more theoretical fundamental physics on the other hand. Do you happen to know the name Sean Carroll?
I do.
Okay. So Sean Carroll's a communicator. He works in cosmology and quantum mechanics, and then he's also a philosopher. But he recently did a 4-hour episode of his show about whether or not there's a crisis in physics based on, different conceptions of the notion of crisis and in different areas of physics. But one field he mentioned as not being in any state of crisis whatsoever is plasma physics, though he didn't elaborate on this at all. So first, just as an aside, I'm curious about whether you think there is, in fact, a crisis in physics or crises in physics in any interesting sense. And then second, why there isn't one in plasma physics, if you agree with that.
Well, yeah, that's an interesting follow-up to what I was saying. I do think that there is some kind of slowing down of the fundamental physics that has been developed over the past 200 years to the point now where we have most of what we think to be the fundamental equations that govern, everything that we have in this universe, and that the prospect of us discovering new laws of physics is much less plausible and is happening at a much slower rate than ever before. And some people think that's a crisis of fundamental physics, in the sense that, well, what do we do next? We can't build, super colliders that reach the incredibly high energies that are necessary to go to the next step in probing, the basic laws of matter and energy. And so experiment in terms of discovering new laws is at an impasse. Actually, I don't think the impasse is particularly severe, even in fundamental physics. I think actually cosmology is one of the areas where we are still able to discover new results that are experimental in a sense and bear on these fundamental questions. But even if there were a crisis at this fundamental level, or at least the sense that there's slowing down, the things in our world that are complex are equally important as the things that are simple. So it may not seem to most people that the laws of physics are simple, but to physicists, we think there is a great intrinsic or fundamental simplicity to the laws of physics, and yet from those simple laws spring all kinds of complex results, including, life and the universe and everything. Okay, and plasma physics is one of the things that springs from those fundamental equations. And plasma physics itself is a very complicated field, and there are new results being discovered all the time, as well as that we're discovering how to apply plasma physics to important human problems and understand the plasmas that are around the Earth and so forth. So we're still very much in a discovery phase of those complexities.
Am I right that much, though, of the complexities of the plasma that you're dealing with now, and we'll get to this more later when we talk about your work in nuclear physics, they're more engineering problems? Is that accurate at all, or are they really purely theoretical problems about how plasma functions?
No, I wouldn't agree they're all engineering problems. I mean, there are lots of engineering problems if you set out to do something specific with plasmas, and the application that has drawn most attention by plasma physicists has been whether we can bring fusion energy to the human scale, and there are many engineering problems that exist within that possibility. But actually, even in that area, most of what's been done in the last 50 years of research on that problem has been basic plasma physics. It's been basic physics. It's been understanding how the laws of physics as we know them work out in practice, and the theories that we do and the experiments that we do, which is also a very important part of physics. Let's not distinguish between theory as being physics and the rest being engineering. That's not true. Physics is both theory and experiment, and these days also simulation. and it's the application of those to practical problems, which is engineering. That's the way I think about things. So I would say that physics is a very fundamental part of what we do in plasmas. There is a division of the American Physical Society, which is the U.S. Society for all physicists, and the membership of that division is as large as most other divisions, except possibly solid state, which is very, very large because of the applications to semiconductor devices of various sorts. And so, certainly plasma physics isn't less a physics field than nuclear physics or high energy physics is, I would argue. And I think that the American Physical Society would agree with me fundamentally. So on the other hand, because of the fact that it is applied physics by and large, there are plenty of people in the field, myself included, who have appointments in the engineering school. So I'm a professor of nuclear science and engineering. My department is in the engineering school at MIT. It's not in the physics department. But that's not unlike lots of other areas of applied physics where applied physicists find themselves in engineering departments rather than in physics departments. Physics is terribly important to society, by the way.
Is.
And I'm not at all ashamed of being in the engineering school.
Right. Well, okay, before we move on, just if I can put my own maybe summary / spin on things and you can respond to just tell me if I'm totally off. But at the very fundamental level, though the classical relativistic picture is very successful in one domain and quantum theory is very successful in another, fundamental physics has slowed down, at least in part. And here's where the crisis might emerge. Because general relativity and quantum theory have thus far remained incommensurable, but plasma and nuclear physics are sufficiently distant from this issue and emerge maybe from the successes of the standard model. And for this reason, it's not subject to the slowing down in fundamental physics.
Well, I think I went along with what you were saying right until your last sentence, okay? Which is that I think it's true that plasmas and nuclear physics are developments of relatively well understood, fundamental, standard model of physics, and that as a result, that their challenges are not subject to the slowing down that has happened because of the difficulty of probing beyond the standard model.